So the whole thing really boils down to the following issue. If you're dealing with a space-time of infinite extent, how do you describe on a finite piece of paper what the properties of the space-time are? In other words, can you have a simple, easy to understand method of trying to understand the entire global structure of infinite quantities? And the answer is yes, and the technique is to use Penrose diagrams to make it easy for you. So the root actually Penrose diagrams were first developed by Carter. I will call them Penrose Carter diagrams. But there was a much better elaboration of the whole subject due to Penrose. So the starting point for this is the following very trivial observation. And that is, if you take a space-time with metric g, you can always discover a new space-time with a related metric, a so-called conformally related metric, g hat, which is equal to some positive function of the coordinates, usually written as omega squared of x, times the old metric. The trivial property is that if you take a null geodesic in this space-time, you will discover that that curve is still a null geodesic in the conformally related space-time g hat AB. So the first question that I need to ask you is, do you know how to prove that? Has it been done? One, two nodding people, I think. So the answer is that you know that fact. So a consequence of this is that under this transformation, you will not change the causal structure of the space-time. It will remain the same. The light codes in the two things are the same. So that is the key point. Now, of course, that's not quite what conformal means. Conformal means angle preserving. Did Dr. Stewart tell you about that? If you think about doing complex geometry in Level 2, in other words, studying functions of a complex variable, you should know this terminology. And you can see it's the same for general relativity. Suppose I take two vector fields, arbitrary vector fields v and w. Then the angle between v and w, in some generalized sense, can be thought of in the following way. Cos squared theta, so this is the angle between them. That's going to be equal to GAB VA WB squared divided by GAB VA VB GAB WA WB by imitating what you have for Euclidean geometry. This, of course, doesn't work if V or W is null. This expression here will give you a slight problem. Notice that if V and W are spacelike, then this thing will be real, and theta will be real, and positive. If, however, V and W are both timelike, this thing will be negative, and so theta will be imaginary. Actually, with my definition, that's not true. This will always work. But this thing is invariant in the conformal transformation. And so if you replace this by G hat AB everywhere, I apologise for using indices like this. I really shouldn't do that. It doesn't matter. So you get here, you could relate this to this. Here you pick up a factor of omega to the fourth, omega squared, so all the factors of omega will cancel out, and it preserves angles. However, if GAB is a solution of the Einstein equations, it is not necessarily true that the conformally related one is a solution of the Einstein equation. So that restricts, oops, yeah, does it still work? In my pocket and it does both for you. And the easy way to see this is to calculate how the curvature tensor and the Ricci tensor and the Ricci scalar behave under conformal transformations. I hope that Dr. Stewart did that. Relevant piece. I did not bring the relevant notes with me to do the conformal transformation. This calculation is a bit of a mess. Now, as things stand, of course, as long as omega doesn't do anything bizarre, an infinite space-time will remain infinite under this transformation. But it could be that omega has zeros or poles, and we'll be interested in the specific case where omega has got poles in it. Under those circumstances, something of infinite size can be mapped into something of finite size. So if G is infinite, then G hat might be a finite size if omega is singular. And the easiest way to see that is just to contemplate the measure. Measuring any integral is b to the half d4x. So under a conformal transformation, that will go to g hat to the 1 half d4x, which is equal to omega to the fourth b to the 1 half d4x. So the measure is not invariant, and so there is no reason why the volume should be invariant. That is a sketch, it's not a proof, because you have to have the right kind of singularities in omega. So the simple thing to do is to look at a very specific example, and I guess that what he actually did was to look at the question of Minkowski space and develop a theory of mapping all of Minkowski space into a finite region of some other space-time, so-called compactification of Minkowski space. Did he explain how to do that in detail? Perhaps on Friday I will tell you how to transport the Riemann tensor and such like, so that you can repeat some of these calculations and some related ones in your own. So, the starting point is the metric in Minkowski space written in polar coordinates. So for me, I'm going to write it like this: minus dt squared plus dr squared plus r squared to the omega 2 squared. Now, of course, if we're going to draw a Penrose diagram, then we have to turn 4 dimensions into 2. And the general way of doing this is just to simply say, well, you're going to regard the 2-sphere here as coming along for the ride. So you want to think of this as being really just the RT plane, and this thing is something which you're going to have to sort of imagine being there. Now, that actually is the source of the problem over the cylinder, I think. So when someone said, well, there was a problem with cylinders and they didn't understand it, it really has to do with ignoring this d omega 2. So, what is the technique? Well, the technique is basically just to simply say, well, I want to, first of all, introduce null coordinates to describe Minkowski space. You know how to do that in the Schwarzschild metric, so it should be even easier for Minkowski space. You define a V, that's T plus R, and U is equal to T minus R, an advanced and retarded time coordinate respectively. Notice that in this expression, R is always greater than or equal to 0, and a consequence of that is that V is always greater than or equal to U. Otherwise, they run from minus infinity to plus infinity. Now, if you want to map all of Minkowski space, where the range of V and U is infinite, into something of finite extent, it is silly to use the coordinates V and U because they have infinite range. It is much easier to use coordinates which have finite range, so then you actually stand a chance of being able to do what you want to do. So I will invent tan P is equal to U and tan Q is equal to V. So I'm going to make P and Q run from minus pi by 2 to plus pi by 2. Since V is bigger than U, Q must be bigger than P, possibly equal to it. And the range of these is pi by 2 to minus pi by 2. So we have at least mapped all of Minkowski space into a finite range of coordinates. So the first step is to express Minkowski space in these null coordinates. Well, if you do that, we should have done something else first. We should have changed Minkowski space of TR to pi coordinates to U and V. That's kind of easy. Since U is T minus R and V is T plus R, the U times dV is equal to dt squared minus dr squared. So the absolute first step here is to rewrite it using that. So ds squared Minkowski still is equal to minus du dv. And then I want to write r squared d omega 2 squared, but I've got to really write r in terms of u and v. So r in terms of u and v is just simply going to be equal to half into v minus u. So when I come over to here, I will end up with a quarter into v minus u all squared d omega 2 all squared. Now we'll do the second coordinate transformation where u is tan p and v is tan q. Du is equal to sec squared p dp. dv is sec squared to dq. So the first term just simply becomes sec squared p, sec squared q, dp dq. So this is still the metric on Minkowski space, but written in these rather unfamiliar coordinates. So you end up with sec squared p, sec squared q, dp dq with an overall minus sign. And then I have to write a quarter into v minus u, all squared. That's sec, or tan, I never know which one is which, actually it doesn't matter. Q minus P. So that's a quarter into V minus U all squared. And if you write this out in a slightly neater way, you will discover this is equal to a quarter into cos P cos Q sin Q cos P minus sine P cos Q all squared. That is equal to 1/4 of sec squared P, sec squared Q, and then there's a factor of sine of Q minus P all squared for this expression. So the metric of the Minkowski space becomes plus 1/4 sec squared P, sec squared Q, sine squared into Q minus P over 2 squared. Now you're in a position to do a singular conformal transformation. You take out this factor of sec squared PQ, the sec squared P, sec squared Q, from there and there. So the conformally related space-time has metric ds hat squared. So it's going to be minus dp dq plus 1/4 sine squared of p minus q over 2 squared. This is already almost recognizable, especially if you've done some homology. First of all, notice that these coordinates P and Q are both still null. So it might be nice to go back to some different coordinates which look more like Minkowski space coordinates, or more precisely, more like Friedmann-Water coordinates. So I'm going to define a T hat and an R hat, and that's going to be a half right. It's not right. No, I think it's right. Let's just check. Q is bigger than P. So this is basically T plus 1. Yes, that's right. So if I turn it the way around, I will discover that Q is equal to T hat plus R hat, and P is equal to T hat minus R hat. So this is sort of like an inverse advanced and retarded time course calculation. In terms of T hat and R hat, you will immediately, hopefully, get ds hat squared is equal to. Well, the first bit is just the same as something we've done before. It's minus dt hat squared plus dr hat squared. And then there's an interesting bit, quarter sine squared of p minus q. That is equal to 1/4 of sine squared 2r hat dt omega 2 all squared. So that is the conformally rescaled space-time. If you stare at this metric, and you've done some cosmology, you will recognize this as a Friedman-Robinson-Walker universe with k equals 1. Meaning that the spatial sections are 3 spheres. And therefore you obviously, as a result of this, compactified space. If you prefer, you can make this look a little bit more like the obvious Friedman-Robinson-Walker universe by putting R hat R bar equal to R hat over 2 and rewriting this thing as ds squared hat squared is equal to minus dt t hat squared plus. Well, I mean 2R hat. So you will end up with 1/4 of the R bar squared plus R bar sine squared. R bar d omega 2 squared. That makes it completely and utterly obvious that it really is a Friedman-Robinson-Walker universe, although with a slightly peculiar scale factor, 1/4. Notice that this scale factor is constant. For a general Friedman-Robinson-Walker universe, you'd have here some function of time, but this thing has got constant size as the cosmological time coordinate changes. This thing is constant. So it has constant size of spatial sections. Now, in a sense, you were amazingly lucky here. You started off with Minkowski space. You were able to find new coordinates easily, or at least relatively easily, these new coordinates. You were able to find the conformal transformation amazingly easy to something which is nice, and end up with a nice metric which you already recognize as something which you've met before. Were you to attempt to do this construction explicitly in Schwarzschild, you would almost certainly completely fail. That's because the analogous construction is amazingly complicated because it's extremely difficult to find the right conformal factor. So therefore, it's important to get an intuitive understanding of what this is about without actually doing serious calculations with conformal factors. That is why one has to spend so much time trying to get used to it. The understanding Minkowski space is in fact the key to the whole thing. Now, presumably Dr. Stewart got to this stage quite happily. So let's try to draw a picture of this space-time. The first thing to notice, I suppose, it is if you look in a book of solutions of Einstein's equations, you'd find this. There is such a book, and actually I suspect you wouldn't find it in it. It seems to contain everything but the simplest possible things. It's usually known as the Einstein static universe. It was invented for the specific purpose of having a static universe. So the idea is that, of course, general universes, even closed ones, tend to expand. So the expansion is, of course, driven by matter. So his idea was to introduce what he called the cosmological constant, to precisely cancel the expansion due to the matter. Hence the story that Einstein's biggest mistake was the introduction of the cosmological constant. Because having invented a universe where this happened, to describe what he hoped would be a static, never-ending universe, Hubble discovered the universe was in fact expanding, meaning that this was a mistake, and you should stick with the matter. So, in actual fact, it has a conceptual problem which is much worse. So, which I will tell you about, even though it's peripheral to the whole thing. Let's first of all try to draw a picture of this. It has its origin R cross S3. The spatial sections of three spheres. Now, I don't know how you expect me to draw a three-sphere, but I have a solution to this, which I think is the solution that causes all the difficulty. I will draw it as a cylinder. Now, that is, of course, a spindle. What I've drawn here is R cross S1. And as every second year undergraduate ought to know, this is not simply connected, and this is. That obviously needs an explanation. So here is a lowbrow definition of simply connected. Can you catch it with a piece of string? If the answer is yes, it is not simply connected. If the answer is no, it is. So, can you catch space with a piece of string here? The answer is yes, you just wrap it around here. Can you catch a three-sphere with a piece of string? Answer no. I can't draw that, which I can draw a two-sphere. which is almost as good. Here's the two-sphere. North and south poles. Can you catch that with a piece of string? Answer no. You can try and wrap it around the equator and pull, and it will fall off.
That's got hard process too.
Well, I just want to think of the S2. You know what I've done. So that's the simple solution to that, and that is in fact the explanation as to why there's a confusion between R cross S3 and R cross S1 and these radial coordinates. So, you have to come to a decision. Dr. Stewart's decision apparently is to say, I say apparently because it's not clear to me that actually what his decision was to say R hat equals 0 is here. And this is what I would decide to do, not what he decided to do. I don't know what he decided to do. R hat is equal to pi by 2 over here. Now, of course, if this was really a circle, then I could go either way around the circle. But it isn't. It's a three-sphere, and so all I can do is to increase R. So if I increase R, it looks like I'm going to go off in that direction.
Can I ask you what it's not R hat equals pi?
R hat equals pi by 2 over here. If 2R hat is equal to pi, and therefore this thing vanishes at R hat equals pi by 2, then R bar would be equal to pi. I would be inclined to call this the North Pole and this one the South Pole. So, by analogy with the two-sphere, we have the North and South Poles there. R hat is the analogue of the co-latitude coordinate, which increases as you go backwards from the North Pole. And it doesn't matter which way you go, it increases. That, of course, cannot be drawn on a cylinder, however hard you try, because it looks like R hat is going to increase in this direction. So this half of the cylinder is kind of fictional, but only in the way in which I draw it. If you really drew an R cross S3, you would, of course, end up with a compact 3-manifold. And if I want to have a compact 3-manifold, the best I can do is a circle. I better not draw an interval. So that's why you end up with a cylinder that looks like that, as opposed to anything else that you might want to draw. I don't want to have a boundary sitting in the space-time. So you can think of this as being going off in the eastern hemisphere, and you can think of this as going off in the western hemisphere, if you like. But it really is all part of the same thing, because you see what you're really doing is you're simply going away from the North Pole. So this division is a bit peculiar, but it's a consequence of trying to draw something four-dimensional, dimension 2. So, hence the cylinder. Now, fortunately, we still have this expression on the board. So, suppose that you sit at R hat equals 0, Q is equal to P, and you go backwards in time as far as you can go in Minkowski space. That sends Q equal to P equal to minus pi by 2. And therefore, R hat is tending to, sorry, T hat is tending to minus pi by 2 plus minus pi by 2 divided by 2 is minus pi by 2. So the infinite past in this picture at R hat equals 0 is someplace here that looks like T hat equals minus pi by 2. Similarly, the infinite future at R hat is equal to 0. Corresponds to T hat going to plus infinity. So that corresponds to P and Q both being plus pi by 2. So those 2 points, if you think about it, represent the infinite future and the infinite past in Minkowski space. So if you're interested in points on this cylinder, which correspond to the infinite past and future, which you arrive at in a time-like fashion, then you'll end up here and here. So this is future time-like infinity, sometimes called I plus, and this is past time-like infinity.
But then you also move R as plus and minus infinity. Go along R.
Yes? Now let's contemplate the effect of keeping R finite. If you keep R finite, but you send T, but if you keep R finite and you send T to infinity, you will still end up at these places. If you send R to infinity and T finite, then you will end up at the point T hat equals 0, R hat equals pi by 2. So that is this point over here. Now, I have to be a bit careful about drawing this. Because I have to be more careful about drawing it. So the green line represents R hat equals pi by 2 on the map. So if you make this surface here T hat equals 0, then this point here corresponds to space-like infinity, where you end up if you go in a space-like fashion. Sometimes called I0, and also sometimes called SPI. Space-like infinity. For some reason that name never caught on. Lastly, you could go to infinity in a null fashion. Either to the past or the future. So under those circumstances, either P or Q is constant. So all such lines will have their boundary, in fact, on the future and past-like codes of these points. So those are easy to draw in this picture. At least easy for people with more artistic skill than me. So, if you start out going in this direction, what will happen is you will go around the back of the sphere, so it's circle, something like that. And if you go in this direction, you will end up like that. And similarly, if you start here, so here, and go backwards, you will end up with a line that looks something like that. And then you will end up there, and on this side, it will end up there. So they all meet up at I0. what you have discovered is that Minkowski space is part of this auxiliary fictitious space-time. And it's this diamond-shaped region that it's the part of. So, what was the achievement of Carter and Penrose? This is that it wasn't exactly old hat, well it was almost old hat when they thought about it. So their insight is that drawing the cylinder is a complete waste of time. It makes everything extremely hard to see. So, what they did was to abolish the cylinder. And instead of drawing this diamond-shaped region on a cylinder, they drew a diamond-shaped region as a little R2. And that makes perfect sense. And therefore, you can identify I plus for this point, I minus for this point, I zero for this point, or perhaps this point. Here, of course, they're drawing up. And here they have been separated. And you might worry about that a little bit. But it's also the case that perhaps you shouldn't worry about it a little bit. Because it's this line that is R equals to 0. R increases out in this direction to, I think we'll call this R hat. So R hat equals pi by 2, and so is this. So really what has happened is if I want to draw it like this on a diamond, I have to think at this point and do the same at this point. And at this point you can either decide to keep the entire diamond or erase the left-hand half. Well, of course, there's all the right-hand half. And that's the problem with the fact that this is a circle, not a free-space. Null infinity is labelled as these points, lines I should say, scribe plus and scribe minus. And so the thing looks like that. Now in this picture, all light codes, remember that conformal maps were angle preserving. I can always construct local coordinates, local inertial coordinates at any point in space-time and construct a light code that looks like a cone with included angle 45 degrees. So in Minkowski space, well, in any space-time, I can always construct light codes that look like this. I've tried to flatten them out into one more dimension and I can really draw. So this is angle preserving, and that means that each point in this space-time I can construct light cones that look like this. Now I ought to worry about the orientation of these light cones, but in actual fact it's very easy. Since the metric is this, I've thrown away that. If I rescale R, then of course this quarter will disappear, and so my light cones everywhere can be drawn pointing straight up and straight down. So they look like that everywhere in the Penrose diagram. Moving space-time to a finite region, compactification, in such a way that the light cones remain at 45 degrees to the vertical or horizontal, are the chief characteristics of a Penrose diagram. So that's what we mean by a Penrose diagram. But in the language of advertising, they say there is more. There is more. First of all, let's contemplate all timelike geodesics. In Minkowski space, all timelike geodesics start and end at I plus or I minus. So a typical geodesic is going to look something like this. Now, of course, I can't easily prove that without solving the geodesic equation in this thing. I'm not going to do that. Just take my word for it. Similarly, all space-like geodesics start and end at I0. So they typically look like this. Or perhaps this. And if I drew it in this picture, they would look like that. And all null geodesics start and end on stripe plus or minus. So that's here or here. So a typical such line, I'll draw in green. In this picture, it will look like that. And in this picture, it will look like that. Do not be confused, however. It is not the case that all timelike curves start and end at I plus or minus. So an example of a timelike curve that does not start at I plus or minus would be this blue one. That is a timelike curve. Of course, it is tending towards something null as you get out here. This would be the trajectory of a uniformly accelerated particle. So it's being accelerated forever. Of course, you could argue you can't really do that, but if you did do it, this is a uniform accelerated particle. So it is not true that all timelike curves have to end at I plus or minus. Although it is true that all null curves have to end at stripe plus or minus. I guess we are completely out of time. Well, that was a bit of a digression. We will return to that whole on Friday.